Okay guys, so this is the third and the last part of the lecture. This is the third video, okay, and it is in continuation with the previous two parts. And with solving these two examples in this video, we will conclude the topic of analysis of rigid jointed frame structures. Uh, there are some new things in this video that you will see. For example, till now we haven't worked out the internal hinge in the frame. Okay, so in this example you will be seeing a internal hinge and what will be the effect of internal hinge uh, when there is an internal hinge in this structure. So it gives you an extra equation. Okay, for example, in the previous example, see, this was the arrangement that you had three reactions, right? And you have three equilibrium equations, the global or general equilibrium equations. These are the three equations. However, with the for example, just keep in mind this video, this figure, the dimensions 32 feet, 20 feet, the loads, everything. Okay, now this is the same frame, right? See, 32 feet, 20 feet, 2 kip, 1 kip per feet, everything. Okay, the new thing is that you have introduced an internal hinge. So this internal hinge will give you an extra equilibrium equation. So in this example you will have four equilibrium equations, and also if you check at the reactions, so there are four reactions. Okay, if there was a hinge, a roller support over here, then the structure was unstable and it couldn't be solved. Okay, but since there are four reactions or four unknowns and there are four available equations, so you can easily solve this. Okay, what you have to determine is the reactions and shear and bending diagrams. So step number one is find the reactions at D and A. Of course, the vertical reaction at D is found by summing moments about A is equal to 0. So take summation of moment at this point is equal to 0. So this force and this force all are passing through point A, so these are will be having zero impact. So you are only left with this RDY, this RDY multiplied by the perpendicular distance, which is 16 plus 16. Okay, and what is the direction of bending moment? It is causing a counterclockwise bending moment, and we have taken it as positive. Okay, now the second is this UDL. This UDL is causing a clockwise bending moment, right, about this point A. So its effect will be 1 into 32 is the magnitude, and it is acting at a center. So the distance from the center is 16. So 1 into 32 into 16 minus this point load. It is also acting and causing a clockwise bending moment. And what is its perpendicular distance? That is 20. Okay, so from this equation you will get RDY is equal to 17.25 kip, and it is upward. Okay, since the value is positive. Now going to the next step and drawing the free body diagram. See, you have removed the supports and you have drawn the reactions RAX, RAY, RDX, RDY, and till now we have only found RDY. Okay, we know its value, and these are the applied loads, and this is the internal hinge. Okay, now next we work with the free body diagram of segment ECD. Which is segment ECD? This is E, this is C, and this is D. So just look at here, this is segment ECD. Okay, now look at segment ECD. We already know RDY, right? So we know the value of RDY, we don't know the value of RDX yet, and the applied load here is only the gravity load. So applying the equilibrium conditions to this segment results in summation of moment about point E is equal to 0. Since E is hinge, see, you can see from here E is an internal hinge, so summation of moments will be of course 0 at point E. Now RDY which is 17.25 from previous slide, okay, multiply by the distance up to E. So you can see the distance of E from D is 16 feet. So into 16, and this is causing movement of in the counterclockwise direction about point EC. RDY is causing a counterclockwise movement, and we have taken it as positive. Minus This 1 into this distance is 16, into half of the distance will be 8. So 1 into 16 into 8 minus this rdx. It has a distance of 20 feet, right? The perpendicular distance. So this 20 is equal to 0. So from this equation we will get rdx is equal to 7.4 kb. Now, in order to satisfy the equilibrium equation, all these forces have to be resisted at the internal hinge point. Why? Because the internal hinge cannot support, or it does not support the bending moment diagram. However, it it resists the shear force as well as the axial forces. Okay, so all the forces will be transferred across this internal hinge except the bending moment. So summation of f of x is equal to 0. We have only two forces in x direction. One is Fe and other is Rdx, and we know the value of Rdx. So Fe will be equal to 7.4 and its direction will be opposite to that of Rdx. Okay. Similarly, Ve, so minus Ve because we are taking it downward, plus 17.25 which is the reaction, and this vertical force which is acting downward we also took it as negative. So Ve is turn out to be 1.25 kips and it is in downward direction. Okay, now with the internal forces at E known, as we have determined the internal forces, axial force and shear force at E, we know these values. Okay, and bending moment is 0 at E, we also know that. So we can now proceed with the analysis of segment ABE. So first we done the analysis of this segment, and now we will move to the analysis of this segment. Okay, so we will draw the free body diagram for ABE. See, this is ABE. We know the values at point E. Here VE was downward, so to satisfy the equilibrium, here VE is in upward direction. Also FE is in the rightward direction, so here it is in a leftward direction. Okay, and we also applied the external forces, and now we will satisfy the equilibrium conditions. So summation of f of x is equal to 0. How many forces are in x direction? This 2 kip, this 7.4, and this rax. So from this equation, the rax turn out to be 5.4 in the rightward direction. Okay, and the second is summation of f of y. So in y direction we have this 1.25 kip and this vertical downward direction applied force and this ry. So we will get ry is equal to 14.75 kips upward. Okay, so we have got the reactions and these are listed in this figure. You can check this: ray, rdy, rax, rdx, and these are the applied forces: 1 kip per foot and 2 kips. Okay, so these are the reactions. Now the next step, what is the next step is to find the end actions at B and C. See, this is your B and this is your C. Okay, so so again, starting from point D. Okay, these are the reactions at point D. 17.25 is the vertical reaction and 7.4 is the horizontal reactions. So in order to satisfy the equilibrium conditions, uh, member CD should be in equilibrium. Therefore, both these forces will be resisted at point C. So summation of f of x says there will be equal force in opposite direction at C, in the horizontal direction, also in the vertical direction. Now these two equal forces and opposite forces at a perpendicular distance are causing a bending moment. And what will be the value of bending moment? We know the direction of this bending moment. It will be in the clockwise. It is causing a bending moment in the clockwise direction, and to resist this bending moment, the same bending moment will be generated at point C in the anti-clockwise direction, as you can see. And the magnitude, you already know that magnitude is equal to this force multiplied by this perpendicular distance, which is 20. So 20 into 7.4 comes out to be 148 kip feet. Okay, now this whole member is in equilibrium. Let me show you that this member CD is in equilibrium. Okay, it is satisfying all the equilibrium conditions. Now, what's next? You have to satisfy the equilibrium conditions at joint C. So here is the joint C. Just draw the reactions. For example, 7.4 is in rightward, so 7.4 will be on leftward. 17.25 is downward, upward. This is anti-clockwise, so this is clockwise. Now in the column section, these are the forces and moments. So in the beam section, uh, apply the equilibrium equations and satisfy them. So 7.4 rightward, opposite to this, 17.25 downward, opposite to this, and 148 counterclockwise direction, opposite to this. So now your joint C is in equilibrium. Okay, you are done with two members. Okay, and same will be the procedure from this side. If you are okay with this, you can come from this side and you can satisfy up to this, and then you can move on to this member BC. And alternatively, you can continue. For example, let's continue from this point. Okay, you have satisfied the equilibrium of joint C. Now, coming to member BC. So, apply the opposite forces as compared to the joint C to make it in equilibrium. So, 7.4 in the leftward direction, 17.25 in upward direction, and opposite to this counterclockwise 148 in the clockwise direction. Now, as I told you before, that all the moments at this point are zero. Okay, so let me first satisfy other conditions. For example, summation of f of x is equal to 0. So 7.4 is in leftward direction. So to resist it, 7.4 will be acting in the rightward direction. Okay. Similarly, 17.25 is acting upward, and 1 into 32 is acting downward. So 32 minus 17.25 comes out to be 14.75. So you have satisfied two equations, summation of f of x and summation of f of y, and you have applied the remaining forces at the other end, for example at end B. Okay, now you are left with only one thing, and that is summation of moments. Now, as I told you repeatedly, and I'm telling you again here, that all the moments at this point will be zero. This means that this bending moment and moment due to this load or shear force cannot be transferred across this point E. Okay, so all the moments should sum up to zero at this point. So let's see, 148 kPa weight is applied in the clockwise direction. Similarly, this UDL, it is causing bending moment in the clockwise direction, okay, about this point E. So what will be the magnitude of it? The length is 16 feet. So 1 into 16 into 8. So that turns out to be 128. 148 plus 128. So it's 256, I think. And these both, why I am adding them, because both of them are in the same direction. Similarly, this 17.25 multiplied by this 16 is also causing a 256, and its direction will be counterclockwise. So this bending moment will cancel out the effect of these two bending moments, and at point E there will be zero bending moment. Got it? So no more moment transfer. So it satisfies the condition of internal hinge as well. Now, coming further to point B, there is only one force, that is this UDL, 1 into 16 into 8. So there is a 108 uh, fit keep fit bending moment that is acting in the which direction? Clockwise direction. Okay, so in order to resist this bending moment, there is an anti-clockwise bending moment that is acting at point B. So now you have satisfied the equilibrium conditions at this point. Okay, and I think I just made a little bit confusion over here. Let me clarify it to you. And that confusion is that I told you that 148 plus 128 is 256. Actually, it is 276. Okay, I just realized that I just mispronounced. 148 plus bending moment due to this UDL is 128. So 148 plus 128 is equal to 276, and the reaction is 17.25 into 16, and that is also 276. So these cancels out each other. Okay, so coming to this point, that 1 into 16 into 8, so it is also 128. 128 is acting in the uh, which direction? Clockwise direction. Okay, and if you remember, let me take you back, and if you remember that at point E there was shear force of 1.25. Okay, and you are considering this 1.25. So this 1.25 multiplied by this 16 is causing a bending moment of about 20 keep fit in counterclockwise direction. So 128 minus 20 is 108. A total of 108 is acting in the clockwise direction, and to balance this, 108 keep fit bending moment should be acting in the anti-clockwise direction at this joint B. Okay, or the point B. Now these are the values at point B: 14.75 upward, 7.4 rightward, and 108 keep fit counterclockwise. Now first we will balance the joint B. So in the beam side, just apply the opposite reactions as you got in the member BC. Okay, and balance them in the column direction. Okay, at joint B, now there is a applied load, external load of 2 kip, so also include it. So summation of f of x, so 7.4 minus 2 is 5.4, so 5.4 will be resisted by this joint. Okay, similarly 14.75 is downward, so apply upward, and this is clockwise, so apply counterclockwise. Now you are done with joint B, and you are left with only member AB. So draw the member AB and transfer these forces. For example, this 5.4 leftward, 14.75 downward, and 108 clockwise, and just resist them at point A. So 5.4 leftward will be resisted by 5.4 rightward. Similarly, 14.75 downward is resisted by 14.75 upward. And the one thing that is left is this bending moment, which is clockwise, and its magnitude is 108 kPa. So this shear force, or this couple, or these two parallel, opposite, and equal magnitude forces acting at a perpendicular distance of 20 feet, they are causing a bending moment in the anti-clockwise direction. Okay, and its magnitude is equal to 108, because 5.4 multiplied by 20 is 108. So at this point bending moment will be 0. So these member forces or member action satisfying all the conditions of equilibrium. Okay, so we can draw this diagram, but for that, in the beam we have to find the point of maximum bending moment. So it is similar to our previous examples, that take a point where bending moment is maximum, and that point is where the shear force is 0. So we take this point of Vx is equal to 0, right? So 14.75 is your reaction at this point, at point B, minus 1 into x, since we don't know the point or the distance where the shear force will be 0, is equal to 0, and x1 will be equal to 14.75. Okay, so at distance of 14.75 from support B or point B, it will be a 0 shear force and maximum bending moment. And how much will be the value of that maximum bending moment? That will be equal to 0.78 kPa. As I'm not repeating these things because we already solved these many times in the previous video as well. So this is your final shear force diagram. For example, in this member it was 5.4 kip shear force, in this member it was 7.4 kip, and in the member BC, it was a beam and there was a UDL applied on it. So there was a 1 degree shear force diagram, 14.75, and or you can come from here 17.25, it's bringing it down, and then 14.75. Okay, and it is happening or occurring at a distance of 14.75, right? So drawing the bending moment diagram, as you can see that these were the hinge supports, so zero bending moment. This was a hinge support, so zero bending moment. This was a hinge, internal hinge, so zero bending moment. So all the bending moments at the hinges were zero. This is the bending moment diagram, this 1 degree diagram or curve. This is for this column, this 1 degree line. This is the bending moment diagram of this column. Okay, and for the beam, this 2 degree curve, this is maximum positive bending moment, which is 0.78. Okay, and then it is coming to 0 at the center, and then it is going to its value of 148. So the beam bending moment is balancing the column bending moment, negative negative. Okay, so these are the shear force and bending moment diagrams for this frame with the internal hinge mechanism. Now moving forward for the last example, and this is called a portal frame with overhang. See, this is your similar frame of previous examples, for example example 4, but the only difference is that you have A, B, C and D, the same frame configuration, right? A, B, C, D. A is your hinge, D is your roller, but you have a small portion of CE, which is overhanging point. Okay, and this is your weakest point. And load is UDL of 15 kilonewton per meter. The lateral load is 8 kilonewton at point or joint B. The vertical height or distance is 6 meter. Horizontal bay width is 10 meter, and the width of this overhang portion is 3 meter. So same requirements that determine the reactions and draw the shear and moment diagrams. Solution results for the various analysis steps are listed below. Take moment at A is equal to 0. We took moment this point 0. So this RAY and RAX, they are not using in the equation because moment is about 0 about this point. We are left with this RD, okay, and this 8 kilonewton and this UDL. So two known forces and one unknown. So we can easily determine from this equation the value of RD, that comes out to be 131.55 kilonewton. Now use other two equations, summation of f of x. Since no other forces in x direction, only this 8 kilonewton and this RAX. So RAX is equal to 8 kilonewton opposite to the direction of applied force, and the third equation, which is summation of f of y, we know RD. Okay, we know the vertical force and only unknown is RAY. So from this equation we will get the value of RAY, that is equal to 63.45 kilonewton. Now what? Now just draw these uh, reactions and find the or determine the member actions. Okay, these are the end actions or the member actions, and start with the weakest point, of course. Just keep in mind that this in this equation or in this sorry, not equation, in this frame or in this example, the weakest point or the weakest member is the joint or sorry, member CE. Member C is the weakest member, and I don't know why I cannot see the cursor. Is it because of oh, what? Is it moving too fast or what? But I am not able to locate the cursor. Let me see what's the problem. It's time is going on, and Okay, so here it is. And CE is the weakest member, and what you have to do is just take its bending moment and apply it here, okay, because nothing can be resisted here. There can be no vertical force here, no horizontal force here, no moment resistance here, because there is nothing. This is a free end, it is just hanging, okay. So just find this bending moment, apply it at joint C. So the tricky point will be that how you balance the joint C, okay. So starting with the CD member, take this CD member, the reaction is 131.55 upward, just apply it downward, and that's it. There is no horizontal in the member or at this point, and since there is no horizontal force, so there is no bending moment generating in the member, okay. Now come to the joint C. This is joint C. You just transfer this force, downward 131 is now upward 131.55 kilonewton, okay, nothing else. And as I told you previously, that you just have to shift this force. For example, this force, what is the force? 15 kilonewton per meter, and this distance is 3 meter, right? So 15 into 3, 45. So your force is acting, and its magnitude is 45 kilonewton. So see, this downward force is acting, and its magnitude is 45, and its bending moment will be equal to 45 into 1.5. So it is acting in the clockwise direction, and magnitude is 67.5. Now this is externally applied load, okay. So you have to balance these three in this beam side, because you are going from weak side to the stronger side, okay. See, uh, let me show in this figure that this is the weaker member as compared to this one, and this is the weakest member. So at joint C, you take reaction from here and reaction from here, and you balance in this member because it is going to the stronger support, okay. So hinge support is relatively stronger than roller support. Therefore, you just took the reaction from here and the applied forces and movement from here, and you are balancing at this side, okay. So 131.55 upward and 45 downward. 131.55 minus 45 is 86.55 kilonewton, and it is acting downward, okay. Similarly, this 67.5 kilonewton meter is acting clockwise, so its reaction will be in this direction, in anti-clockwise direction, okay. Now you have balanced the joint C. So going to member BC, just apply these forces and moments in the opposite direction. For example, this counterclockwise will be clockwise, and this downward will be upward. Now just make this member in equilibrium, and it is very simple. Summation of f of x, no f of x, summation of f of y. So 86.55 is acting upward, 15 kilonewton per meter is acting downward. You know the total length is 10, so 150 minus 86.55 is equal to 63.45 kilonewton. Similarly, at this point, at point B, there are three bending moments. One is this applied bending moment in the clockwise direction. One is this 15 kilonewton per meter into 10, 150 into this 5, okay. And the third one will be anti-clockwise movement, and this is 86.55 multiplied by 10, so 865. So when you subtract this and this moment from this one, the remaining or the resultant moment will be in counterclockwise direction, and its magnitude is 48 kilonewton meter. So to balance this, a 48 kilonewton meter bending moment have to be acting at point B in the clockwise direction, okay. So now your member BC is in equilibrium, and you have to move to joint B to make it in equilibrium. So at joint B, just draw the forces and moments in opposite direction. For example, this upward will become the downward, and this clockwise will become the anti-clockwise, okay. So you also put it the applied horizontal force, which was 8 kilonewton at joint B, and now in the column segment you have to balance it, because you are going from weak side to the stronger side. So this 63 downward is now 63 upward, this counterclockwise is now clockwise, and this rightward is registered as in the leftward direction. So your joint B is in equilibrium. What's next? Move to member AB. So before going further, you just shift these forces to point B in the member. Okay, so 8 leftward is 8 rightward, 48 clockwise is 48 anti-clockwise, and 63 downward. Upward is here downward. So satisfy the equilibrium equations. 8 kilonewton rightward, now 8 kilonewton leftward. 1, 63.45 downward, 63.45 upward. 2, what about this bending moment? So here you got 8 kilonewton, right? Acting at a perpendicular distance. How much is the perpendicular distance? 6 meter. So 8 into 6, what will be the direction? Clockwise. So this anti-clockwise will be resisted by this clockwise. So this 48 kilonewton meter bending moment is resisted, and there will be no bending moment at joint A, which satisfies the uh, our concept that there will be no bending moment at hinge support. So this is how you got the what the end actions in all the members. So again, in the beam we have to look at the point of maximum bending moment, and for that we have to look at the point of zero shear. The same equation, and from here it is 4.23 meter, putting it here, and you will get the maximum bending moment value as 182 kilonewton meter. Plotting the shear force diagram, the constant shear force 0 degree in this section. There will be no shear force in CD because the D was roller support and it cannot resist horizontal. 1 degree shear force in the overhang section, which was CE, and 1 degree of shear force diagram of the beam. Okay, and similarly, the 1 degree bending moment diagram in this column, 2 degree in this overhang section, and 2 degree in the beam. And we know the value of maximum bending moment, and where it is happening is 4.23 meter. So this was all about the analysis of rigid jointed frames. I hope I have tried a lot to convey the basic concepts, and using different examples and different boundary conditions with different loadings with different arrangements. I have tried my best to convey the message, to convey the concept that how to analyze the frames. And I know that it is very difficult to understand 100% with this mode of instructions, but what I could have tried, I have tried my best, and hopefully, if you go through this lecture 1, 2, or 3 times, you will get the concept. Thank you very much, and see you next time.